Thank you. Thank you, Noah. I'm Takenobu Toyota from Hokkaido University, Japan. So today I would like to talk about the recent observation we conducted using a drone in the marginal ice zone in the Sea of Okhotsk. So in this presentation, I will pay special attention to floesize distribution for small flows and melting processes. The outline of my talk is shown here. And first, I'd like to start my talk by introducing the research trend on this topic. So, floesize distribution of sea ice significantly affect the behavior of seasonal ice zone, both dynamically and thermodynamically. And thermodynamically, it controls a melting rate, especially in the marginal ice zone in spring, where relatively small ice flows dominate. Because for the same CS area, smaller ice flows have longer perimeters. So in the marginal zone, small flows are produced due to breakup through wave ice interaction. Besides, not the CS area is usually composed of various sizes of ice flows, as shown in the picture. This picture was taken in the Sea of Okhotsk. So it's also important it can provide fundamental properties of CS dynamics. So it's also important for CS dynamics. So major science questions are described here. Are there any systematic characteristics and what controls the evolution of floesize distribution? And how floesize distribution affect the dynamics and melting? So recently, with the development of observation methods, the attention to floesize distribution is increasing. Many measurements were conducted, like here, conducted to clarify the statistical properties in various regions. And also, a theory has been developed and even applied for the climate model. As the CCA showed this morning, the previous presentation. So, however, we still need more data to elucidate the formation and the melting processes, especially at small scales. For the Sea of Okhotsk, although floesize distribution ranging from 1 meter to a few kilometers was revealed to some extent by our previous paper, and the change of properties was observed at about 40 meter and 1 meter. But at that time, a question remained about, especially at the 1 meter, the change at the 1 meter. It presents the effect of lateral melting or the limitation of the horizontal resolution. So the purpose of this study is to validate it and also clarify the floesize distribution at meter scales, which would represent the melting at the final stage. So we conducted the observations in February 2020. So in 2020, sea ice extent expanded southward to the Hokkaido coast in early February and began to cover the southernmost area of Sea of Okhotsk on February 6th. And here, so the observations of floesize distribution were conducted using a drone launched from the patrol vessel Soya at 6 sites along the ship track and coordinated with hydrographic measurement with CTD and wave V development during the February 10th to 13th in the southernmost Sea of Okhotsk. Since the ice flows available for the analysis from this measurement could be found only sites, another 6 sites located here in the vicinity of open water. we focus our analysis on this site in this analysis. So this figure shows the drone track and images from A to G captured with a PC software for the analysis. And the flight height was set to 50 meters for all the site. So for just for information, this figure shows the representative ice conditions at each site. And you can see only at site number 6 site, small ice floors, which is available for the analysis, can be found. And the observation at number 6 was conducted in the afternoon on February 13th under the clear sky conditions with air temperature of plus 0.2 degrees Celsius, wind speed of 2.4 meter per second, and near surface down to 20 meter depth. Water temperature of approximately minus 1.4 degrees Celsius, which is well above the freezing point, minus 1.7 degrees Celsius. So thus, the analytical result provide a good opportunity to investigate the lateral melting processes of sea ice at the final stage. To extract the individual ice flows from the images, we conducted image processing with the PC software, following basically the previous method by Toyota et al. 2006. So this is because the validation of the result is one of the purposes of this study. And the procedure analysis is summarized here. Firstly, conversion from the RGB to grayscale. And the horizontal resolution is about 2 centimeters per pixel. And decision of the threshold between sea ice and seawater, and manual correction to extract the individual flows and check the result from the original video images, and analysis of individual flows with the PC software. So since the brightness of the image is subject to various features, such as rich shadows on the ice surface, so procedure 3 was the major part of this analysis. When we magnify the part of this image and overlap it to the original figure, you see it matches well with the surrounding sea ice area. So it means that it has similar properties. So in the analysis, special attention was paid to the self-similar properties following the Rothrock and Thorndike in 1984. So here, the flow size is defined as the diameter of a disk that has the same area as that of the flow. So not limited flow size distribution. The right-hand figure shows the flow shape or flow geometry also has self-similar properties. The upper figure shows the scatter plot between the maximum size and maximum minimum size for individual ice flows. So you can see a high correlation between them and the averaged ratio, which means the aspect ratio is about 1.73 or 2. And the lower figure shows the scatter plot between the size defined from area and size defined from the perimeter. And if these parameters are equal, the ratio of this parameter is 1, it shows that the shape is perfect circle. So with the increase of the ratio, increase in the ratio, it means the degree of distortion will increase. So we call it the distortion index. So you can see a very good correlation between them. So the results are represented in the form of cumulative number distribution, n, which is defined by the number of flows larger than d. If n is cumulative number of flows, the power law flow size distribution is supposed to be self-similar mathematically. Since nearly the same results were obtained for all the images, all the results were compiled together in this figure. So actually, this figure contains 4 kinds of lines. Actually, the scene, 5 scene lines drawn for individual images, a bold line for the compiled data, and a broken line for the underlying power law, and the red bold line for the power law function, including the truncation effect expressed by this equation. We need to include the truncation effect because the number, cumulative number, counts the number of the flow from the maximum size of flow. So it depends on the size of the analytical image. So we should subtract the truncation effect. And here, the upper truncation size, dt, is set to 9.0 meter, which corresponds to the 99.9 percentile of all the flow size data. And the coefficient C and exponent alpha were calculated by the optimal interpolation method for ice flows larger than 0.8 meter. The reason why we selected 0.5 as a lower threshold is shown here. Here, we magnify this part here, and you can see the deviation occurs below the 0.8 meter. So in the end, we found a very good coincidence between the borderline and the truncation per law function. So it means that it has a similar properties. So in the end, alpha was estimated to 1.35, which is intermediate value for flows of 1 meter to 1 kilometer in size compared with the part result. So also flow shape and flow geometry also has a similar properties as shown in the previous slide. Here, I'd like to mention about the geometry of ice flows, focusing on the aspect ratio. Here, the aspect ratio obtained in this study is close to the past result obtained for larger ice flows, as shown in this table. So interesting is that the aspect ratio is similar irrespective of regions and flow size, which suggests that the processes for shaping flow geometry might be relatively common irrespective of region. Here, we examine the size dependency of flow geometry in more details. In this figure, the aspect ratios and distortion indices of all the ice flows are plotted as a function of flow size. This figure clearly shows that the flow size, the flows with higher aspect ratios and highly distorted flows increases significantly below 0.8 meter. Inside, so here we discuss what determines the threshold of 0.8 meter. Based on the past studies in the Arctic Ocean, we assume some dynamical breakup is responsible for the change in flow size distribution below 0.8 meter. If we can assume that the likelihood of some dynamical breakup is controlled by weakening of sea ice due to the increase in sea ice porosity, the likelihood for the some dynamical breakup would be expressed by this equation. by this parameter. So in this parameter, F is the heat flux at unit ice surface area transferred from the surrounding seawater to sea ice. And A is the ice surface area contacting seawater. And delta T is the elapsed time, and rho is ice density, V ice volume, and Q is the heat of fusion for sea ice flow. The denominator denotes the total heat needed to melt the sea ice completely, whereas the numerator shows the total heat absorbed from the surrounding seawater. Since the parameter is proportional to A over V, and A over V can be calculated in this way. So the flow size distribution would become significantly important for this relationship. It means the flow size is less than 4 times ice thickness. Since the ice thickness is about 0.2 to 0.5 meter around this area, the threshold would be about 0.8 meter. I think so. In that meaning, it would be reasonable. So next, we discuss the lateral melting rate and processes. For this purpose, we followed the method by Felch and Jones in 2014, who estimate the lateral melting rate from the temporal change in flow size distribution. They showed from the observation that the exponent alpha increase according to the thermodynamic breakup process. And at the same time, the lateral melting occur, and the lateral melting amount was estimated by comparing the change of the flow size distribution. Assuming the lateral melting amount is the same for all the ice flows, they calculated the cumulative temporal evolution of cumulative number flow size distribution. And by comparing the data, they estimate the lateral melting rate as about 6 centimeters per day. And in one case, here I will explain our case. Here we assume that the effect of lateral melting and thermodynamic breakup begin to be prominent both for the same threshold, because the both are attributed to the efficient heat absorption from lateral area. So assuming the lateral melting occurs evenly for all flow sizes, this figure shows the expected changes in flow size distribution for 4 centimeter and 10 centimeter. And by comparing with the observed data, the optimal value is estimated as 4 centimeter per 6 days. It means about 1 centimeter per day. From this equation, the total heat of fusion required for the lateral melting is calculated as 25.3 megajoule per square meter. Next, we try to evaluate this estimation using meteorological reanalysis dataset, ERA5. To evaluate this estimation, we calculated the hourly surface heat budget in the open water from the solving equation, from this equation using ERA5. The calculation period is from February 6th, when the sea ice started to cover this area, to February 13th, when this observation was conducted. So when this result was a net heat input in the open water. When we take the summation of the data, it shows the negative value. But if we take the summation of the positive value in the daytime, it gives 33.7 megajoule per square meter. By comparison, the heat needed for the lateral melting is estimated as about 75% of the heat input in the open water. And based on the floesize distribution, the CS area fraction covered with flows from 0.2 meter to 9.0 meter is estimated as about 50%. So this result suggests that the estimation of 4 centimeter is reasonable, and the heat absorbed in the open water area in the daytime should have been transferred efficiently to sea ice flows, partly to melt them and partly to increase the inner porosity. Now, I would like to summarize my talk. From the floesize distribution was conducted in this area for the first time using a drone, and under the very calm and warm conditions. And the cumulative floesize distribution of sea ice larger than 0.8 meter basically followed the per roll. So, and the exponent and the aspect ratio of the individual flow were estimated at 1.35 and 1.73, which lies in the range of past range for large ice flows. It shows the self-similar properties. And floesize distribution of sea ice flow less than 0.8 meters seems to have been affected by some dynamical breakup, and which could be represented by a simple lateral melting model. And heat budget analysis with ERA 5 shows that the total amount of lateral melting is about 4 centimeter. It corresponds to the 1 centimeter per day, and comparable with the 75% of the total heat gain in the open water, suggesting the efficient heat transfer from the surrounding water to the sea ice. Okay, that's all. Thank you very much. Thank you for your attention.
Thank you very much. Any questions? Yes, Pat.
Yep, very nice talk, Takenobu. Just a quick question. Can you comment anything about the snow depth distribution on the ice flow? Are they uniform, or you see some variability at this scale? Yeah, thank you.
I mean, you mean as a variability?
Yeah,
so
of
you mean
the snow and albedo of the ice flow at this scale.
Okay. Okay, I don't know the exact answer, but the small, now we are focusing on the small ice flow. So the small is quite small. The effect of snow is quite small. So I think it enhances the absorption of the heat in the sea ice area. So that also contributed to the efficient transfer of heat to the sea ice floor. Is that okay?
Yep, okay. Yeah, thank you again for your talk. Yeah.
Thank you, Alberto.
Thank you very much for the very nice talk. And I like the point that the future work is measurement of FSD for uniform sea ice, like pancake ice.
Yeah.
Some of the work that I've done in the past.
Yeah.
It would be interesting to look at those data, and if it's, are you planning to do for the soil and the Okhotsk Sea, I guess?
Yeah.
And one of the main points of that paper was that we couldn't fit really a power law. We had a peak at a certain specific diameter, and it would be interesting to see if you get similar results in Okhotsk.
Actually, the main purpose to start this study is actually I wanted to know the pancake floesize distribution for pancake ice because it would provide some implication how the pancake ice is formed, affected by the wave ice interaction. So it's a major purpose of this study, actually. But actually, unfortunately, it's quite difficult to come across such a special case in the institute observation. And also in the pancake ice form, here the pancake is forming, the wave is a little higher, and it's quite difficult to fly the drone. So it also hamper the observation. But actually, I know your paper, and I'm very inspired by your paper. And I also interested in how the flow size is distribution is formed in such a beginning of the CS formation. So I think that will be a future work. And if we have a chance to, we want to do that,